Good morning and good evening, everyone. This is my project for the week 9 on Digital Integrated Circuits under Sir Garcia. And the topic is about the design of a two-input multiplexer using a double-pass transistor logic circuit. Let us first discuss the advantages and disadvantages of using a double-pass transistor logic. So one advantage is that the DPL is used to avoid non-full swing problems on the pass transistor network, and also it is used to improve circuit performance at low supply voltages. It also has a simple design and has a low contribution to static power. The DPL has its advantage that overcomes the problem of the complementary pass transistor logic, which is regarding about the voltage degradation and noise margin. The DPL has also a balanced input capacitance, and the area of implementation and the cost consumption is less. And it is ideal to use this circuit on XOR and multiplexers. The disadvantage of the DPL is that the NMOS pass transistor is incapable of passing a good logic 1 due to the threshold effect. And for the PMOS, it's also not capable of passing a good logic 0. So we may find poor performance also if we use the DPL in and or circuits. So this is the double pass transistor logic schematic diagram. So we can see here that we have for the and the NAND, and on the below is the XOR and the XNOR. In my project, I used the NAND gates. The schematics is similar to this one, and we can notice that we have an input A and B and a complementary input for the A and B also. And output is complementary, and the supply is located here. So for the design of the two-input multiplexer circuit using a DPL, what we have here is the block diagram for the two-input multiplexer. Here we have the A input selection, and on this pin is the I0 and I1. So the main function of the two-input multiplexer circuit is that it takes multiple analog signals. In our case, we have uh, two channels here, and forwards the selected input to the output single line channel. So that is the job of the A input, which selects what channel, if I0 or I1, will be forwarded to the output. So here we can analyze the truth table of the two input multiplexer circuit. Considering the A input here, we have a low state and a high state. For the low state, the circuit is selecting the I1 channel, as we can see here. Then this is forwarded to the output. Then for the high state of the A input, this circuit is selecting the I0 channel here, this range, and forwarding it to the output. We can verify that using this plot, or the for the graphical representation. We have a T1 to T8 here, and this is the A input and the I1 and I0 inputs, and Q is the output. So the low state, we are selecting the I1, and this is forwarded to the output. You can see here. And for the high state, we are selecting uh, the I0 here, and it is being forwarded to the output. So that is for the input multiplexer circuit. So this is my design on using the electric software. I use the PMOS and the uh, CMOS transistor here, and on this the circuit, maybe I can separate it by blocks to explain what this what is this circuit is, what is the part of this, what is the parts of this circuit. So first, let me explain this block. So on this block, use for PMOS, the width and length ratio is 1.6 over 0.35 microns, and NMOS is zero point 0.8 over 0.35 microns. Then on this block also, we can see that this we have an inverter here for the A input. Then the selection input, we have a data stream using the pulse of 0.3.3, 0 nanosecond delay. Then rise time and fall time is 1 nanosecond, and the period is 200 nanosecond with 50% duty cycle. The supply of the circuit is 3.3 volts. Then for the I1, this is this block. You can zoom. I1 here is DPL, the DPL circuit, and this is the DPL circuit. Then this part is the inverter. So why I include an inverter here is that we need that because for the DPL there is a complementary input here on this side. So it is necessary to include an inverter here. So this is the input. This I1, this I1 circuitry here, the input is coming from this data stream. So the pulse is zero to 3.3 volts, delay is 0 nanoseconds, rise time and fall time is 1 nanosecond. Then the period is almost half of this pulse. So 50 nanosecond to 100 nanosecond, that is 50% duty cycle. Okay, let's try to check another block. So in this case, we are checking the I zero. Then this is the non non gate part, the last part. Okay. So on this part, same. I use width over length 1.6 to 0.35 microns, and for the NMOS, I use zero point 0.8 to 0.35 microns. We can observe here that the length is less than the width. So the effect of here is the improved propagation for the signal. So the length is kept at minimum. Okay. For the I zero, the same circuit we can observe like on the I1 part. So I zero is almost same, but the the data stream that I've using is the less period. So in this case, I have a 25 nanosecond to 50 nanosecond or 50% duty cycle only. Unlike for the input for the I1, I have 50 nanosecond and 100 nanosecond. Then this is the output part. We have a capacitor here, 100 microfarad. Then I use transient analysis about 300 nanosecond range. Then the sampling is around 500 picoseconds. Uh, we need to zoom this one, this part. Okay. Then finally, this is my simulation results from that circuit. We can observe that the response is similar to the logic truth tables. Let us check if okay. Uh, for the input A channel, this is the high part and this is the low state, the high state and the low state. Okay. So if we have a high state on the A, we are selecting I1. Sorry, we have a high state on the A, we have a high state on the A, we are selecting I0. High state on the A, we are selecting high zero. So for on the I0, we have a high, low, high, low. So this will be reflected on the output. So high, low, high, low. Okay. For the low, low state on the A input, we are selecting the I1. So in this case, we have a longer time period on the high and the low of the I1, then it is reflected also here on the output. So in that case, we have a similar response versus from the logic truth table. So our simulation is good. Okay. This slide is about the transistor sizing. So let me discuss the things to consider on the transistor sizing, the width over length ratio. So the first thing is that an increase in the transistor size is directly proportional to the speed up of the CMOS inverter. And another thing is that the current in the MOSFET is proportional to this ratio. So if we consider to minimize the transistor area, so the first thing some people do is that the length is kept minimum, then they adjust the width. Then regarding the width of the transistor, if the width is increased, then the peak current or the current drive will also increase, and this will result to a decrease in the rise time and the fall time when driving a capacitive load. But also we should keep in mind that increasing the area will result to the increased input capacitance. Then this is the trade-off. Then from that will slow down the transitions at the input node. So it is better to simulate if we are tweaking the width to length ratio. Then lastly, the shorter the length, the faster the transistor will switch. So the propagation will be faster. So here are the some common width over length ratio, which is the 3 is to 1, 2 is to 1, 1 is to 1. But depending on the manufacturing process technology node. So for 3 is to 1, we have 250 nanometer, 180 nanometer. We should be using 2 is to 1. Then for 10, 20 nanometer, should be using 1 is to 1. Then also I try to simulate the width over length ratio, which is a 2 is to 1 simulation and a 1 is to 1 simulation. For the 2 is to 1, I have a specification of zero point 0.7 over zero point 0.35 microns. And but if we compare that on this specification, the only change is that the length from 0.35 we change it to zero point 0.7, and we can see this result. The output is somehow have a propagation delay higher than the 2 is to 1 ratio. So that is the effect of increasing the length. So increasing the length of the transistor will result in longer rise and fall time. This is due to the increased resistance to the path of current flow. Also have an effect that dropping in the operating frequency. So that would be all. That is the regarding this topic. That will be the my final slide. Thank you for listening.